I'm introducing folks.
Go for it.
Let me know when you're live.
We're up. I've been up for like 2 minutes already.
Okay.
Need a whistle.
Hey, it's time to start.
Listen up.
On behalf of the Colloquium Committee, I am happy to kick off the first iteration of this year's Faculty Flash Talks. So we're going to have 5 faculty members giving a brief update on what they're working on, or what they work on in general, or whatever they feel like talking about. As you'll notice, we have lots of prospective grad students visiting this day, so this is a bit of introduction to some of what's going on here, as well as a reminder of what we're working on. So up first is Hannah Zanowski, I think. Yeah, you're up first.
John's always in the way. That's something you'll learn about him. All right, so I am Hannah Zanowski. If you did not catch that, I'm an assistant professor here at the Department of Atmospheric and Oceanic Sciences. I am in my 3rd year. Yes, 3rd. Okay, it's 2.5. I got it, right? And I am a physical oceanographer. And my favorite part about being in this department is being one of the squeaky wheels of oceanography to make all of our atmospheric scientists in here care a little bit more about the ocean. So, a little about me. I grew up in Arizona. I've lived in a bunch of different places before I ended up here. But here is where I am now. So I got my BS in math and physics from the University of Arizona. And then I went on to get my PhD in atmospheric and oceanic sciences from Princeton. I did a postdoc at the University of Washington as part of the Joint Institute for the Study of the Atmospheric Ocean, which is now SEACOS, or PSYCOS, sometimes people like to pronounce it. I think it's SEACOS. And then I did a second postdoc at the University of Colorado Boulder, working at INSTAR. And then I finally came here. So I've kind of jumped around a lot, but I've definitely questioned myself a lot as I went through that process. So if that is part of your journey, it is totally okay. All right? And in fact, it's normal. So this is my group right now. I have a research group. That's also really exciting. This is me. All right? This is Marissa Trippish. She's my very first graduate student, hanging out in the back there. And then I have 2 undergraduate students, Ella Wickstrom, who works with me. She's doing a senior thesis with me, and then Ivana Chevalier, who's been working with me this year as well. All right, so this is my little group, and I am very, very proud of it. All right, and the whole thing that we do in our research is ask this question of how do the oceans ocean? All right. So let's get into that a little bit. And you'll start to realize why I have such a broad theme for what I do, and it's because I do way too many different things, all right? So I use climate models to do my research. I like to use them, I don't always like to run them because they're a huge pain in the ass, but they're a really cool tool to look into the future and potentially look into the past as well, all right? So I have 3 themes for my research. First one is polar oceanography. So my background in my PhD is actually Antarctic oceanography, and thinking about the connection of what happens around Antarctica and how that is actually communicated into the very deepest parts of the ocean, all right? Using a lot of climate models to do that. But since then, I have moved entirely into the Arctic, where I kind of ask questions about basically what is the Arctic Ocean doing currently, and what is it doing in the past, what did it do in the past, and what is it going to do in the future, right? So the Arctic is one of the fastest changing regions on our planet. And so understanding sort of the oceanography of this region is really important. And so I ask questions basically about how sort of the ocean sort of transports maybe things like heat and salt, and just straight up volume, so actual water, in and out of the passageways of the Arctic. So how does the Arctic Ocean actually communicate with the other oceans? So the Pacific Ocean over here through Bering Strait, as well as the Atlantic Ocean and the Bering Sea opening, Franz Strait, and the whole 9 yards. All right, so it's kind of one theme. Second one, though, is paleoceanography. So big question for me is how did the physical and chemical oceanography of early Earth actually impact climate and potentially the origin of life on our planet, all right? So big change from polar, right? So I'm doing currently some like mid-Holocene paleoceanography work, which is actually work from my postdoc. Like your postdoc just never ends. You keep collaborating with their old advisors and it just continues on into like a weird snowball of too much stuff that you do, all right? At least for me, because I love to drag things out, all right? It's my favorite, all right? But I have started to kind of think a lot about what happened, or how did the ocean circulate on Earth when it first formed. So the ocean actually formed about 3.8 billion years ago. Okay, so it's been around for a really long time, and it is actually coincident, more or less, with the earliest known life on our planet. All right, so those two things are potentially linked, and I really care about asking those types of questions. So you can use ocean models to do that, and that is the work that Marissa is doing. She does ocean circulation on Archean Earth, and so the Archean period is this period from about 4 to 2.5 billion years ago. And at that point, Earth was more or less a water world when it first formed its ocean, all right? So there wasn't really a significant land masses, so not the continents that we see today, which deeply impact the actual circulation of our ocean, all right? So we can ask questions then about how that matters, how the potential bathymetry at that time matters. Shout out to Liz, who thinks about those things too, but not at that time period, more present. As well as kind of eventually thinking about the sort of chemical oceanography side of things. I am not a chemical or biological oceanographer, but one day I'm gonna know some chemistry for the ocean, all right? That's the cool part of being a professor, is that you can teach yourself new things and you will learn them, all right? Last thing I do with exoplanet oceanography, I am also starting to kind of enter into this realm. There are oceans beyond Earth that are inside our solar system, so on icy worlds like Enceladus and Europa, so we're thinking about moons around Jupiter and Saturn. Ganymede probably has an ocean, Triton probably has an ocean, Pluto might have an ocean under the surface. You keep going and going and going, there's oceans everywhere, this is like my dream. So I like to think basically about what sort of sets how the ocean basically sets climate, or not necessarily sets climate, but modulates climate and potential habitability of exoplanets, all right? So there's also a lot of potential ocean worlds out there, so exoplanets that are fully covered by oceans outside of our solar system, and now we're in this realm with JWST, or James Webb Space Telescope, where we can actually start to get atmospheric spectra from some of these exoplanets. So we live at a very exciting time in terms of that. But for me, I just want to model it all because that's what I know how to do. Right? So who knows, maybe years down the road I'll be doing something completely different than this, but that's just how it goes. All right, a couple other things you might want to know about me. I teach also, it's a big part of my job. So I teach the Computational Methods in Atmospheric and Oceanic Science class. This is AOS 573. It's basically a class where you learn Python to do earth science data analysis. Super fun class. Apparently it's very useful for certain graduate students, is what I hear, John. Thank you. Yeah, all right, appreciate that, you guys. I teach Introduction to Physical Oceanography, or the Fundamentals of Physical Oceanography is what I'm going to call this. It's a 400 level, like get into the nuts and bolts of the physics of how the ocean works, all right? At the undergraduate level, and then this semester I'm teaching for the first time a GEO or AOS class. It's 105. It's a survey of oceanography, which is basically just an introduction to sort of not necessarily science majors about basics of the ocean. So from plate tectonics and sediments and geological oceanography to chemical and biological and physical oceanography. It's just a very general non-math sort of explanation and exploration of how the ocean works. All right. I also lead and actually developed the research experience for undergraduates program we have here in this department. It is called STORM. Thank you very much. I did come up with an acronym, and it's Student Training in Oceanography, Remote Sensing, and Meteorology. I did not, however, create this amazing logo. That goes to Marissa and many of our graduate students who put this together, all right? So we do have an REU here. We bring students, 10 students every summer to get involved in research. This is our first official cohort just from this past summer. We will have another one this summer, and hopefully for many, many more years to come. I have a fearless co-PI on Chris Side, who is our department chair. And then, of course, this would not be possible without all of our amazing graduate students who do a huge lift every summer to sort of help keep this program together, help keep it running. So I will leave it there because I don't know how much time it took. So thank you. That's me. Okay. I saw it and I was like, oh, I'm just going to make fun
Up
of
next
Dan.
is Dan Vimont, and I should also mention that I have timer for 10 minutes because these are our flash talks.
Oh,
thought there were 5, so.
Even better. Well, if you get to
Yeah,
10.
Me too.
No, 5 is good.
I got 3 slides. I don't know
Well,
what
in
I'm
that
supposed
case,
to do.
let's talk about fishing for a little bit. All right, I'm the worst looking of the 2 organisms on the image. That's a Snake River cutthroat caught in the mountains of Wyoming. My name is Dan Vimont. I'm a professor. I've been here for years and have been and have loved it. I teach a variety of different courses here. I started off teaching some of the statistics courses, and I have developed a sort of the graduate level statistics and then a advanced statistics course here. I teach a couple of ocean atmosphere interactions. I also teach the 100 level weather and climate course, and then a variety of other courses sort of based on so that's some of the ways that I might interact with you as a graduate student in the classroom, also fluid dynamics and so forth. So a little bit about me. I grew up in the Pacific Northwest, ended up going to Gonzaga University. Go Bulldogs! Not doing so great this year, but Bulldogs anyway. I'll tell just a quick story. So I rowed at Gonzaga University, and then I went to University of Washington to study oceanography and atmospheric sciences, ocean atmosphere interactions. And then we came here, and I started my career here. And one day, as we were driving back from northern Wisconsin, it was winter time, and we're driving down from northern Wisconsin back home, and I'm drifting into oncoming traffic as I'm looking over my shoulder at one of these rivers. I said, "Honey, that river was frozen over on the way up." Only a couple of days earlier. And when the screaming stopped, as we finally came back into our own lane, there was this moment of silence, or it was a couple of minutes of silence. And those of you who have a significant other, when there's those 2 minutes of silence, they convey a lot of information. And my wife looks at me and she says, "You're really into water, aren't you?" And I realized it was one of these moments that kind of she looked deep into my soul, and I was like, yes, I really am. I really enjoy fluids, water, and so forth. So and fishing, yeah. But part of that fly fishing is also watching the creek and so forth. All right, so here's a couple of things that I do. This is a couple of projects I have going on right now. One is looking at tropical ocean atmosphere variability, and we're doing this using a variety of different models. Well, this is one example of a model that last April I thought, well, we're doing all this analysis, let's see how well it does in forecasting and so variability. So we made a forecast in April. This is the initial condition in April. There wasn't a whole lot going on in the tropical Pacific at that time, but there was a lot of warming off the coast of Peru, and there was a lot that was going on in the subsurface ocean, and that was really critical. We made a forecast, and we forecast a 1.8 degree Celsius ENSO event for this December. And I started talking with folks at NOAA, and they said, none of the statistical models that we have are forecasting a strong El Nino event. All of the dynamical models we have are forecasting a strong El Nino event. And this, which is a statistical dynamical model, is consistent with those strong, the dynamical forecast models. So this is the forecast for December, and this is what actually happened. So the actual Nino 3-4 index ended up at a 1.2 degrees Celsius total. So it nailed the forecast for this. So one of the reasons why, and so I'm excited about that for the fact that it's kind of fun doing the forecast and stuff, but also because that particular model takes advantage of the fact that variability occurs around a seasonal cycle. And almost all the work I do looks at the interaction between that seasonality and the kinds of variations that we see in the climate system. So what we've done is we've developed a series of models that infer the dynamics of the system based on the output that such a system would create. So that system may be the real world. And so we use what are called inverse methods to back out what the model that produces that variability would be. There's a benefit to that because we're actually estimating the real world. The downside of that, it makes it hard to run physically based experiments. So we also use forward models, large-scale global climate models and so forth, to test some of the hypotheses that we see and that we make based on these empirical models. So we use a variety of those, and we're also in the process of developing new techniques for estimating new forms of stochastic dynamical models. One of the other projects I have, this is looking at the seasonality of global warming. Turns out that in the North Atlantic and the North Pacific, the warming since 1970 is about 40% larger in the summertime than in the wintertime. So summers are warming a lot faster than winter. And when we look in global climate models, it's ubiquitous across climate models that the same thing is occurring. By the end of the century, most of these climate models show about a 3-degree warming during the wintertime and a 6-degree warming during the summertime for, say, the large scale, or for the rapid warming scenarios. So one of the things we're looking at is why is that occurring? Is it due to the forcing itself? And so we're looking at sulfate aerosol forcing. How does sulfate aerosol forcing get transmitted across the Atlantic? What effect does it have? What are the radiative effects of that sulfate aerosol forcing? How does it interact with clouds? How does that change in radiation affect the global climate system and the historical evolution of climate variability that we've seen? How does it impact feedbacks? What are the seasonality of the feedbacks? And developing, again, these stochastic dynamical models, simple models of the mid-latitude oceans to try and understand how these, why we see that change in seasonality. That has a big impact on things like marine heat waves and other ocean phenomena as well as atmosphere. And last, one of the other areas that I've been very active with is looking at climate impacts. And so we put together an organization about 15 years ago called the Wisconsin Initiative on Climate Change Impacts that brings people together to try and understand how climate change may affect folks here in Wisconsin. And I always say that as a climate scientist, as an individual, I'm the wrong person to tell anyone about what's going to happen with climate change or what decisions to make about climate change, because I don't know how people are going to use that information or how people use information. And so together, once we start a conversation, then I learn what's important, and we can start defining new research ideas and defining metrics or research topics that allow us to converge on information that's relevant for people who are using it. And so we've set up Wiki, sort of unfortunate acronym, although I guess it's fitting, as this big decentralized conversation that brings people from all sorts of different communities together to have the conversation that allows that catalyzes the emergence of research questions and progress in understanding climate change. And actually, I am leaving immediately after this to go talk about the effect of climate change on building design conditions for, with a bunch of HVAC engineers immediately after this. So I do have to leave immediately after that. But that's an example of that kind of conversation that's sort of ongoing with Wiki. I like it a lot because it brings community into what we do, and it brings people together. I love thinking of climate change as a way of bringing us together as a community. Something that I'm really proud of here at AOS, hoorah, AOS, and something that I think you'll find pervades a lot of what we do. Thanks, everyone.
Oh, okay, 10 minutes. Professor Hitchman.
Okay, yes, I'm Matt Hitchman. I grew up in mostly Portland, Oregon and Bellingham, Washington, and then attended the University of Washington, got my PhD there. I worked on the weak-mean flow interaction problem in the tropical middle atmosphere, but I've enjoyed looking into all sorts of other kinds of things since then. I worked at NCAR on forecasting the fate of ozone for 100 years, and then decided to try it here, which was 1988. So I've been here for a while. What I'd like to do today is just highlight people's discoveries in the last few years that people have been working with me. In order of who I met first, Shelley Rowe, she's been working on stratosphere-troposphere exchange, tropical cyclones, derechos, she's a researcher too. Dan Forte is working on his MS, and he should be done pretty soon, focusing on Atlantic tropical cyclones. Yingchen Sun is a PhD candidate, doing a very careful study of various kinds of QBO indices. And then Wenyan Du, he's an undergraduate researcher, and he has actually calculated refluxes from a data set and published it in de novo. And he's also a co-author on a QBO paper on the QBO coming up. It can happen in just 6 months, actually. He started working with me last summer. So the first topic is the QBO direct effect on the UTLS, then the origin of tropopause folds, or one way that they can occur. A little bit about how there's a PV dipole in derechos that nobody really knew before, which Shelley found. And then the diurnal cycle of the UTLS PV variability in the tropical cyclones, I think, is a pretty interesting topic as well. So here we go. This thread in the literature comes from Gray et al. In about 1991, and then Chip Trepke did a PhD with me here, and so I learned this is his idea. If you apply the Plum and Bell circulations of the QBO to the tropopause, it deforms upward and downward in an antiphase sense in the tropics and subtropics. So if you're in the westerly phase, you have westerly wave drag causing supergeostrophic flow, which is convergent, so it goes down and you create a warm anomaly from that. But there's a return mean meridional circulation with cool anomalies flanking it. So descending regimes of QBO westerlies will cause a warm anomaly in the tropics, cool flanking adjacent subtropics. The reverse situation, during QBO easterly shear, you have rising motion, a cool elevated tropopause in the tropics, but a warmer lower tropopause in the subtropics. Some things that really jump out is if you look across data sets, this is the NSEP data set for about 20 years, and you can see near centers of convection, the difference between westerly and easterly QBO for tropopause temperature is significant, where it's cooler in the subtropics on average and warmer in the tropics in tropopause. This one is 100 hectopascal temperature, similar pattern, cool during westerly in the subtropics, warm in the tropics. And then MERA2 also shows that same signal. And if you want a really strong signal, then you might want to look in southern winter. This is tropopause pressure, 6 millibar difference in tropopause pressure in the subtropical southern winter. Or March, April, May is astounding. Really big differences in the temperature at 100 hectopascal. Here's the zonal wind, 3 to 5 meter per second enhancement of these jets during QBO westerly. The Walker circulation is also strongly affected by QBO westerly. And the way to think of this is, here's a temperature pattern associated with these marine meridional circulation patterns, and it's a tic-tac-toe grid of 9, and it slowly descends with time. So if you know right now that it's QBO westerly, then you know what the wind anomaly is here in the subtropics from this map. And this whole pattern smoothly descends with time. And there's not just two equal and opposite phases. Easterly and westerly are not the same. Westerly shear and easterly shear are also 1/2 of the time record. So it doesn't make any sense to throw half of the time record out. What we're hoping to do is to show that a 4-phase QBO index is superior to the other ones. And this is how this pattern looks in wind anomaly. So Yingchen Sun, here's just an example of his careful plots. He can compare the EOF method, where you take 2 phase angles and a central averaging angle, all of which are parameters, and he's done detailed, careful studies of this, comparing a 4-phase method, a 2-phase method, and an EOF, which are actually all in there, but it would take a long time to explain, so I won't at the moment. He has an abstract in to the Burlington Middle Atmosphere meeting, which will probably be interesting. And then here's Wenyan Du, the past 6 months. So he published this data set in Zenodo that he created from ERA5 data, EP fluxes and their divergences that people can use for other climatology studies. And then he's an author on this paper here, which shows, these are his calculations, that during neutral and ENSO years, if you look at the climatology, EP fluxes go upward and equatorward, but they're diminished during QBO westerlies. And the difference shows a convergence pattern that's present in both El Nino and neutral conditions, but not La Nina. And what that means is more energy is going up into the middle atmosphere, and it modulates the amplitude of the planetary waves in the UTLS in the mid-latitudes. Here is one way to get a tropopause fold. You can take an east-west snapshot, and here's the subtropical jet coming out of the page towards you. These are contours of potential vorticity, so we'd say this is stratospheric air underlying tropospheric air. And what happens is, if you look at detailed numerical models, the vertical motion field here and here is about the same, which is very close to zero, but it's diabatically cooling slightly in the polar air mass. But one way you can get a tropopause fold, which looks like this in the previous cross section, this is idealized. So we can take a bowl shape of stratospheric intrusion and then carve it out on one side, and when the air goes around it, you can carve it out on the other side, getting a classical tropospheric intrusion pattern. How does that work? In the upper troposphere is where you have a maximum westerly wind speed. So it'll go more eastward underneath stratospheric air and also over underlying stratospheric air that was previously in place. So it just routes it out by going more straight and creates this pattern. And that's due to a momentum surge, or just a jet streak and speed maximum. Here's the topic of the Iowa derecho. We used 3-kilometer high-resolution rapid refresh model forecast analysis and compared it. We used absolute vorticity, which is what they have there. PV in 4-kilometer resolution UW-AOS simulations, and what we found is that the updraft coincides with a maximum PV anomaly, and the downdraft coincides with a negative maximum, which is inertially unstable. And the westerly jet comes in, the inflow jet, and turns to the right, descends and blends with a polar outflow from, equatorward outflow from a lower tropospheric anticyclone and creates a meridional jet. So the strange thing about derecho is twofold. Nobody ever pointed out the meridional jet before, which is really noticeable. Here's the sequence of radar reflectivity for this event, and we can see that when winds went from 5 meters per second to 35 meters per second, what happened to the wind direction? It went from 270 to 360 and stayed northerly or northeasterly after that. That is to say, the gust front at a derecho is from the north, not from the west. It's sort of a new thing. And so if you look in HRR data in the east-west section, here is the descending nose of strong westerly flow. Here's the axis of the meridional jet coming out of the page toward you. It lies in the downdraft. Here's the updraft. And then we have a pair of PV anomalies, the positive PV anomalies in the updraft, the negative PV anomalies in the downdraft, and they're separated by the southward jet, which is kinematically what you need to have. That if you have a jet, you always have a PV dipole and vice versa. Here's some schematics showing parts of the situation. You have a westerly inflow layer. Here's the southward jet in between. Here's the PV dipole with the southward jet in between. And here's a perspective view of this meridional jet that extends southward, creating the outflow gust front and the PV dipole pair. Here's the schematic. If you look down on it, if you have a southward jet, you have to have this. It's just kinematic. But these are produced by diabatic processes. The last topic is Hurricane Yasa. It grew and it waned. And so we studied the life cycle of it and found a really notable diurnal cycle in the mesoscale variability of potential vorticity as provided by the European Center for Medium Range Weather Forecasts. And these are 9-kilometer global data set. So we have started to look at many tropical cyclones from this point of view. And what you see is a peak in the early morning, 8 Kings locally, in the early morning, 6 a.m., 6 a.m., 6 a.m. After reaching magnitude 2, I'm almost done, the amplitude really decreases, but it still is a diurnal cycle, and there's a peak at midnight. And all of this is consistent with theoretical expectations from diurnal cycle of radiative theories of tropical cyclones. Some people get really upset with this and say, no, well, that's not true in absolute vorticity. Well, it is. All you have to do is divide PV bar by zeta plus F, and you get the static stability factor, which just does this, and right at 100 hectopascals, it jumps by a factor of 20, and that's why PV has a large amplitude. This signal here is exactly the same in absolute vorticity variance, just multiplied by static stability. So you can look at time height sections following motion, which are really interesting. See key points, but I'm over time. So I want to highlight Daniel Fortier's contribution to this is really nice. He composited 15 tropical cyclones, and the ones that were over Cat 2 in the Gulf region also show a peak in PV variation in the UTLS in around midnight with a minimum in the afternoon, which agrees with a lot of other types of diurnal cycles. All right, thanks for listening.
Yeah, I get to introduce myself. See, I started with a slide that doesn't have my name on it, which was, probably not the best place. I'm Elizabeth Maroon. I'm interested in broadly how do the oceans impact climate and vice versa. So I'm just to tell you about one slice of the research that me and my group are doing here. And we're going to start with something that, research-wise is my first love, which is the Atlantic mural overturning circulation. I also really like bad disaster movies. So when I was in college, right, we watched The Core. What other bad ones did we watch? What else was coming out bad? College bad. Yeah, Twisted. Well, that's well before.
Did we watch 2012? We didn't watch 2012?
No, I didn't watch 2012 in college. But The Day After Tomorrow. So the whole premise behind The Day After Tomorrow is that the ocean circulation collapses, and within like a week, the whole world freezes over because you've got air that's coming down from the stratosphere that doesn't adiabatically warm. It just comes down cold, straight, and freezes the entire world. And the
Suspension of the first one.
Yeah, the
Exactly.
cooling rate's on descent. It's in the
Yeah,
movie.
yeah.
Cooling up on descent.
Yeah, something like that. Air warms adiabatically. Anyway, Day After Tomorrow. But there is actually a premise for this, which is that over glacial cycles, we know that there's been the changes in ocean circulation and how much heat it transports poleward or not, and that this warms or cools the northern hemisphere high latitudes relative to the tropics. So the ocean circulation is important. However, could it really happen, that quickly? So you're saying, climate change shut down the North Atlantic Ocean circulation, just like this movie, and abrupt climate change. So I'm going to tell you about the day well after tomorrow, which is a funny way of saying just some of the research that I'm interested in, some of the results from the last couple of weeks even, and my interest in the North Atlantic Ocean. So Friday is when I was putting this together, and Friday there were some great headlines. Atlantic Ocean circulation nearing devastating tipping point. Here's the day after tomorrow. Melting ice could cause chaos. Same paper. Critical Atlantic Ocean circulation system is showing signs of collapse. So this gets back to that day after tomorrow scenario, that ocean circulation is really important for the stability of climate, and that there could perhaps be abrupt climate changes that could really change the climate state. All of this is, there was a new study that came out Friday, and the media loves this topic. So broadly, I'm interested in many things, but one thing I'm interested in is North Atlantic Ocean circulation and its relationship to climate. So when I say North Atlantic Ocean circulation, I'd like to have a schematic. So here's a schematic from the Buckley and Marshall review paper, a fantastic AMOC review paper, you haven't read it. North Atlantic Ocean circulation is composed of, at the surface, the Gulf Stream, which detaches from the North Atlantic coast somewhere near Cape Hatteras, goes northward, and then it gradually turns into the North Atlantic Current, where it makes another left-hand turn towards Greenland, then a couple of right-hand turns. Some of it loops back to the Lav Sea, according to the schematic. Some of it goes up into the Arctic, where it's transformed from light, warmish surface water into deeper, cold, dense water, which is indicated by these blue arrows. So some of it comes back out of the Nordic seas, depending on which flow it's coming out of. Some of it loops back through the Labrador Sea as a deep western boundary current, where it comes down back into the subtropics. This is a very, highly idealized schematic of North Atlantic circulation. But you'll notice that there's kind of two ways you can understand this. One is all of the horizontal aspects of it, which are the gyres, and then there's the overturning. So the fact that water at high latitudes, in the North Atlantic at least, sinks. So I'm going to tell you briefly about just one quick result from 2 projects I'm working on related to the overturning circulation in the Atlantic. One is a model intercomparison that is using process-oriented diagnostics, which is to say, some way of understanding the climate system that isn't just a simple field like temperature or salinity. Instead, we're using overturning stream function as a function of density. You can ask me after this, why density? And trying to relate it back to other parts of the climate system and how it's related. So what I've got here is, this is from last Tuesday. This is not even a week old, this result. So on the x-axis, I've got overturning strength, and on the y-axis, I've got subpolar North Atlantic temperature from 0 to 200 meters. Each color indicates a different ocean model from the Ocean Model Intercomparison Project. And as you can see, there is a pretty nice linear relationship here. It's like, oh yeah, we got something to study, right? So these are all models. The real world's Atlantic overturning circulation is probably about there, so strength here. So you can see that not all those models can be right. And the temperature of the subpolar North Atlantic is kind of up there. They're all in reality, up there. So they're all a bit too cold. So what we're trying to understand here is, how are these biases related? How is overturning stream function, how is it wrong in models? And how is that related to other features of the model? In this case, a very well-known cold bias in the North Atlantic. Another thing I'm working on in that project that's just starting up is using idealized global climate models to understand what is the impact of, in this case, a fundamental process, which is flow that's being deviated by the Mid-Atlantic Ridge. So I've got some preliminary simulations where we take out the Mid-Atlantic Ridge. So this is the control. Mid-Atlantic Ridge is this bathymetry feature right there. It spans from the South Atlantic all the way up to Iceland. And then this is our simulation, which we have called Flat Atlantic. You'll note it, yes, I thought that was pretty good with it. Flat Atlantic. You can see the Mid-Atlantic Ridge is gone. So why might you want to study this? Well, there's a lot of key places where the bathymetry interacts with the circulation. One is, it steers the flow up in the subpolar North Atlantic. Some of it gets steered around the Reykjanes Ridge, so it tries to go westward. Some of it depends on where they're at fracture zones. So the North Atlantic Current has preferential locations where it'll go eastward, depending on if it's the wind forcing and if it's aligned with the Charlie Gibbs fracture zone or other fracture zones. So bathymetry is important for circulation. And I will end this with the really quick result that I have one simulation where I don't have an AMOC. I don't have overturning at all when I take out the bathymetry. Is something going on in that simulation? Is it initial condition dependency, or is bathymetry a really key part for the stability of our ocean? And I'll leave you with that, and hopefully I'll have a paper out later this year that you can see the answer, though it might take a little while to really get to the answer to this. So, thank you for listening, and up next is Ángel Adames Corraliza.
All right, I'm the last one, so I'm gonna be quick and hopefully we'll be out. As you can see, my title doesn't have my picture. I opted for Klaus. You can just look at me if you want to see a picture of myself. As let's mention, my name is Ángel Adames Corraliza. And yeah, my research group is on tropical weather systems and climate. And I just arbitrarily chose this picture of clouds because they're pretty. But they kind of get the point across home about the importance of especially these types of clouds and convective clouds elements over here. So a little bit about myself. I'm originally from Puerto Rico. I studied physics at the University of Puerto Rico, Mayagüez, and then just moved around all over the place. I don't need to give you the details about it. But at some random chance of life, I ended up here, and I'm giving this talk to you guys today. So why study the tropics? So if you go to any old book of tropical meteorology, they'll describe the tropics as this like paradise, pleasant place where nothing really actually happens other than rain and occasional hurricanes. And as we've kind of gotten more adept and gotten more observations, especially satellite observations, we've realized that that's actually not the case. There's actually a lot going on in the tropics, and I'm not going to bother you with what these contours are, other than telling you that these are different types of tropical systems that are seeing in this animation of cloud brightness, as you see on the right. You can find the full animation on my website, ifadames.com. And this animation, the main point that I want to drive you home with this animation is that there's actually a lot going on in the tropics at any given point in time. There's actually a lot of activity, a lot of different tropical systems. And this is actually counter to this old way of thinking, which the tropics is just mostly clouds and occasional hurricanes and not really much going on. So we discovered that all of this actually is going on. So why? You might be asking yourself, why? Why is so much going on in the tropics? Is there any particular reason for seeing so much activity in the tropics, especially encountering with this old way of thinking that there may not? Long story short, we do have work on that. You can go to my website and check it out. It's a little bit on the complicated and theoretical end, which brings back to what our group does. So my research group has a bunch of people. I'm going to show a picture later, but this is what we kind of do. We combine theory, observations, and modeling to try to answer these like pressing or maybe not so pressing questions, depending on who you ask, about how the tropics behave and what is their ultimate role in our climate system. So we do a bunch of different topics. So here is some of the non-exhaustive list of things that we study. So we do tropical waves, MJL, monsoon depressions, TC formation, tropical convection, El Nino, climate change. Here's a picture of some of the people in my group. I couldn't get everybody, but you know, here's a nice picture from like AGU and from my student HC's defense. We're happy people, or at least we look happy in these pictures, maybe not on a day-to-day basis. You know, research can be difficult sometimes, as you will, all of you will soon find out. You know, it's a joke, but it's also like not a joke. You know? So this is my group. This is what we do. I didn't put that much in. You can always talk to me afterwards, but I also wanted to mention that I do teach courses, as Hannah mentioned early on. Here are the courses that I teach, and not related to, except I teach geophysical fluid dynamics, which I'm teaching right now. I also teach Introduction to Atmospheric and Oceanic Physics, which is mostly a thermal course. So if you are enthused by all this talks today, and you really love it here at UW-Madison, then guess what? You're probably going to have a year of classes with me. And especially like in the 24-25 year, we're already kind of scheduled that in. I also teach advanced tropical meteorology, which we teach occasionally. So if you're really, really, really into this, then you can take a full course with me, and you can go crazy with me, and we can learn more about the tropics and the role of the climate systems. And look at this picture here. Isn't this picture beautiful? There's a bunch of tropical waves with developing into tropical cyclones, and this is why the tropics is wonderful. Thank you.
Okay, I think that concludes our flash talks. Thank you all for coming. In lieu of questions, why don't you just come and ask us questions, because I think we'll probably stick around here for a little bit. And have a nice afternoon.